This global industrial footprint represents a staggering energy baseline. Every day, demand for crude oil reaches nearly 104 million barrels, with projections pushing that total to 105 million by next year. Yet, in its natural state, this volume is industrially inert. Crude oil is a chaotic slurry of liquid hydrocarbons, a disorganized collection of molecular chains formed from organic fossils over millions of years. High-performance engines and synthetic materials require precision that geology cannot provide. They depend on specific molecular geometries, such as the branched isoparaffin shown here. Bridging this gap is the work of the refinery. It is a three-stage thermochemical process designed to deconstruct and then rebuild these molecules through separation, conversion, and treatment. To follow this process, we have to track how chemical engineers restructure these prehistoric hydrocarbon chains at the atomic level. Crude oil serves as a vast reservoir of raw atomic building blocks, the basic inventory for a high-precision molecular assembly line. The process begins as extracted crude enters the massive processing infrastructure of the refinery complex. The first stage, separation, occurs within these distillation towers. It relies on intense heat applied by a furnace to begin the sorting process. Inside the column, a strict temperature gradient, hottest at the base, coolest at the top, forces molecules to separate by boiling point. Heavy, compact fractions remain liquids, pooling at the bottom. Lighter fractions evaporate, rising through the gradient until condensing in cooler other tiers for extraction. Fractional distillation is a physical sorting method, leaving the refinery with an imbalance, a surplus of heavy residue, and a deficit of usable volatile fuel. Addressing this gap requires chemical intervention. In the conversion phase, we move past physical limits into chemical architecture. This matrix tracks our two primary variables: chain length on the y-axis and structural branching on the x-axis. The priority is size reduction. Cracking breaks massive, heavy fractions into lighter fuels. Fluid catalytic cracking uses a fluid-like powder catalyst to shatter these chains. On our matrix, the heavy molecule drops vertically as bonds are severed, yielding lighter products like gasoline and LPG. Thermal cracking uses extreme heat to achieve similar results, though it leaves behind a heavy coke residue used in graphite and carbide manufacturing. Hydrocracking offers a more efficient alternative, producing light distillates without leaving any residue behind. While cracking solves the volume problem by creating more raw fuel, it does not address the combustion stability required for high-performance engines. Stability depends on the octane rating, which is determined by how branched the hydrocarbon chain is. Straight chains burn too quickly, leading to engine knocking. Alkylation solves this by building larger, complex molecules. An olefin and an isobutane molecule mix with an acid catalyst, forcing them to bond. This creates an isoparaffin. On our matrix, the molecule moves into the high-branching quadrant, becoming a high-value component for increasing octane. Polymerization fuses light hydrocarbons into a high-octane blend. Alternatively, isomerization and reforming rearrange existing molecules. They physically snap and reattach carbon bonds without changing the molecule's overall size, moving the paraffin horizontally across our matrix from a straight to a branched chain. The conversion phase functions as a chemical forge, ensuring the refinery's output is engineered for energy density and stability. Even perfectly shaped molecules are flawed if they contain natural contaminants. Raw crude typically carries sulfur, nitrogen, and iron that must be removed before the product is finished. In hydrotreating, chains enter a 380 degrees Celsius reactor with sulfur and nitrogen atoms attached. Pure hydrogen is pumped in, aggressively severing the contaminant's bonds. Nitrogen converts to ammonia, and sulfur to hydrogen sulfide gas. Both are removed, leaving a pure, stabilized paraffin chain. Without this chemical wash, these fuels would carry corrosive impurities that damage engine components and release sulfur into the atmosphere as acid rain. Zooming out from the molecular level, this vast coastal footprint functions as a single, massively scaled chemical equation in continuous operation. Thermal separation sorts the raw fractions, catalytic conversion manipulates the carbon bonds, and hydrotreating strips away atomic impurities. These newly engineered molecules are stored in specialized silos, ready for global distribution. These refined hydrocarbons are the essential precursors for the petrochemical industry, providing the raw material for products like rubber, synthetics, and plastics. Specialized transport networks then move these high-value finished products into the global market. The modern industrial world depends on this daily, high-speed dismantling and rebuilding of millions of years of geologic history.